Hello everybody, in today's video we're going to be analyzing trigonometric equations. What that means is we're trying to solve essentially for one variable, and typically solutions are typically in one rotation of a circle, but technically there are actually going to be multiple solutions sometimes, right? So therefore there are times where a solution is like an inequality or an equation is always true, sometimes true, or never true. Okay, so take for example, if I were to have sine x, and let's say I made it equal to cosine x minus pi over 2. Okay, so in this particular case, if I were to draw sine x, it'll essentially look just like this. Okay, right? So in this case here we have 0, we have pi over 2 right over here, we have pi, 3 pi over 2, and you also have 2 pi here. Okay, so if I were to graph cosine x minus pi over 2, what this tells me is that my cosine is going to start at pi over 2. And essentially what that's going to look like is I'm going to start here, because remember cosine always starts at the top and the maximum or the minimum value. And as you can see, it's still, the curve of the cosine is exactly the same as the sine here, right? This part here is exactly the same, and if you were to continue sine, it would still keep going on that trend. So in this particular case, both graphs are basically the same, and what that means is for any x value, it's always going to be true, right? So that's what it means by always true, is when their graphs are essentially what we call coinciding with each other. So when two equations coincide with one another, basically what that means is sits on top of each other. Okay, that's one way to look at always true. Right? When it comes to sometimes true, so in this case, let's say I had sine x is equal to 1. Okay, so in this case, let me graph both sides again. So I'm going to graph sine x right here. Right? And remember, the base sine equation has a maximum of 1 and a minimum of negative 1. And if I were to graph 1, right, that's going to be essentially just a horizontal line here. Okay, and as you can see, these graphs only intersect at this particular point. And when you look at this, this is actually going to be at pi over 2. So what it means by sometimes true, that just means there's a limited number of solutions. So in this particular case, this is going to equal to, so we're going to say that x is equal to pi over 2. Because that's where sine x is equal to 1. But if you take a look, if I were to continue this further, and if I were to draw a longer straight line here, as you can see, I'm going to have another solution here. This solution in particular is 5 pi over 2. Okay, where in this case, it actually repeats itself. One way to look at it as well is if you take a look here, this is at sine. This is when sine pi over 2 equals 1. Okay, as you can see, that's when it equals 1. But if I were to do one full rotation, so let's say I started from here and I ended up doing one full rotation, okay, I still will end up having an angle that will give me sine is equal to 1. Okay, so what that means is if I were to have sine pi over 2 plus a full rotation, which we can call 2 pi, right? If we are more comfortable with degrees, I can say 90 plus 360 degrees. Okay, I'm going to get, if I were to plug this angle in for sine, I'm still going to get a 1. Okay, so in this case, if I have sine 450 degrees, that's still going to give me a giant 1 here. So what does that tell me? That tells me that no matter how many cycles I do, like full cycles, I'm still going to get the sine of that angle is equal to 1. So some ways we can write it is that x is equal to pi over 2, because that's the first time we see a 1, but essentially I can keep adding rotations, which is symbolized as 2 pi, as many times as I want. In this case, n represents the number of cycles. Okay, so like in this case here, this one right here is 1 full cycle. So when I plugged in n is equal to 1, I would get this solution that I have here. Okay. So essentially, if you find one solution, all you have to do is plug in this 2 pi times n here, and then essentially you get your answer. We'll take a look at more examples in a bit. Okay, and that's, so in this case, this equation is sometimes true at these x values here. And of course, when it comes to never true, let's say sine x is equal to 2. Right? If I were to graph sine again, here I have 1. And if I were to plug in 2 right over here, there's no intersections at all. Okay, this graph will never go all the way up to 1. So in this case, we can say that never true means that no intersections between each equation. Right. So we have always true, meaning that there's the same exact graph essentially. Sometimes true when both equations intersect at specific points. Never trues mean they don't intersect at all. So let's take a look at a few examples here. Okay, so right over here we have this equation here. So something you notice is that, remember, sine squared x is the same thing as squaring sine x here. Okay, so one thing we should do is try to get sine by itself. So in this particular case, we have, I can divide 4 to both sides. So we have sine squared x is equal to 1/4. Okay, and then to get rid of the square, all you need to do is square root both sides. Therefore, I end up getting sine x is equal to plus or minus 1/2. So this one's very important because, like we say, if we wanted to get 1/4, I can multiply either 2 negative 1/2 or I can multiply 2 1/2. So that's why I wrote it like this. So now you might be thinking, how are we going to get the solutions here? So in this case, what I'd recommend is to look at the unit circle. Okay, so please recall that sine x is essentially the y coordinate on the unit circle here. So we want to look at the y coordinates that have 1/2. And as you can see here, this is one of our solutions. So 1/2 is in the y coordinate, therefore this has to be a solution. So if you take a look at here, oh look, we have another one. We have 1/2 here, that's also another solution. So in this case, 30 degrees or pi over 6 is a solution. 5 pi over 6 or 150 degrees is a solution. But we also want to consider the negative version. So the negative, we have this one here. We also have this one here. So we have more negatives. So essentially, we have 4 solutions in one full cycle so far. So let me list them out. So x is pi over 6. It's also going to be 5 pi over 6. it's also going to be 7 pi over 6. It's also going to be 11 pi over 6. Okay. So what this tells me is that if I were to, that means just like what I wrote over here, if I were to do a full, starting at this angle here, and I do one full rotation, I'm going to get another answer, another angle that will give me a 1/2. So in this case, if I were to start at pi over 6 and I do a one full rotation, this is going to be my solution. I'm going to write this essentially for every single solution that we have. Okay. So I got pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, 7 pi over 6 plus 2 pi n, 11 pi over 6 plus 2 pi n. And these are all for the solutions. Okay. Something you can do, yes. So now I can do the same exact thing for tangent. Okay, so I can divide by 3. I get tangent squared x is equal to 1/3. Square root both sides. I end up getting 1 over root 3. Okay. So something to remember is that tangent, remember, is just sine x over cosine x. So one thing we could do here is figure out when is sine gonna give us a 1 at the top, and when is cosine gonna give me a root 3 at the top. Okay. And some of the special lengths that we've come to know is 1/2 and root 3 over 2. So essentially I can rewrite 1 over root 3 as 1/2 divided by root 3 over 2. So essentially you want to figure out this combination. If we have this plus or minus here, it's very important. So now I need to figure out, oh, okay, when is cosine root 3 over 2, and when is sine also 1/2? Okay. So in this particular case, let's take a look. Remember, cosine is the x, sine is the y. So let's take a look at the first quadrant here. Oh, would you look at that? We have cosine here, and we have sine here. So cosine is root 3, and sine is 1/2. So in this case, that's also another solution, right? Same thing over here. Cosine is negative though, but as you remember, I can have a negative solution. So in this case, A and B actually have the same exact answers here, right? Because of this combination here. So in particular, the answer for 3 tangent squared x equals 1 is basically the same solution as this first one. Okay. But this next one is a little bit more tricky because it requires a bit more algebra. As you can see, we have a mix of 2 different functions. I have sine, I also have cosine. So we kind of want to treat them as like their own separate variables. Okay. So because right now we can't, it's kind of difficult for us to solve it. So let's think of them as variables. So one thing I can do is, this one here is a term, this is another term, and they both have sine in common. So one thing I can do, I can factor out that sine, thus giving me sine x times 2 cosine x minus 1. Okay. So I factored out the sine because, remember, sine is being multiplied to both of these terms here. So now, one thing I can do here is I can use a zero product property. Because I have 2 factors being multiplied together and they equal 0, that means sine x could be 0 to make this true, or 2 cosine minus 1 can equal 0 to make this true. So essentially, I split this up into 2 equations. I have sine x equal to 0, and then I have 2 cosine x is minus 1 is equal to 0. Okay. So Now I just need to solve for both of them. And as you can see, if we look at a unit circle, when is sine x equals 0? So remember, sine is the y. And as you can see, there's two solutions here. Okay. So for sine, for this first part, x is equal to 0 radians, but it's also going to be pi. See that? X is also equal to 0. X is also equal to pi. And then we can just add the 2 pi n because it's going to keep repeating. Okay. And this one right here, I can simplify this a little further. So if I were to get cosine by itself, we end up getting cosine x is equal to 1/2. Okay. So now I just need to figure out when is cosine 1/2. And remember, cosine is x coordinate of the x value. So in this case, right over here, cosine is 1/2. And right over here, cosine is also 1/2. And those angles here are pi over 3, which is 60 degrees. So x is pi over 3 plus 2 pi n. And the last one is going to be right over here, 300 degrees, which is same thing as 5 pi over 3. So 5 pi over 3 plus 2 pi n. And those are going to be solution for C. Just like that. Okay. So the very last one here involves the reciprocal equation, reciprocal function. So we will want to go about it the same way. One thing we can do is try to get it to a form that we are familiar with. So secant is the reciprocal of cosine. So what I can do is I can rewrite this as 1 over cosine squared x. Okay. Because secant squared x is a reciprocal function, I can write it as 1 over cosine squared x. And then essentially what I will do is I would try to get cosine squared x by itself. So this right here simplifies to, if I were to multiply cosine to both sides and then divide 4 to both sides, we're going to get this. I'll end up getting 1/4 is equal to cosine squared x. And it's going to work similarly to these other ones. I would square root both sides. So I end up getting cosine x is equal to negative 1/2, plus or minus 1/2. Okay. Then we want to do the same thing. And we already figured out over here cosine is equal to 1/2, and these are the solutions to that. So let's go ahead and kind of just rewrite that. But now we need to figure out the other one. So cosine is negative 1/2, and that's right over here. We have a solution right over here. We also have the other one right up here, which is at 2 pi over 3. We have one at 4 pi over 3. So in this case, the other solutions are 2 pi over 3 plus 2 pi n, and the other one is going to be 4 pi over 3 plus 2 pi n. Okay. So as you can see, we've graduated from finding only one solution, right? Like we could have easily just used the inverse of cosine, but that's not going to capture all of the solutions. Using the relationship between the unit circle and the angles and doing full rotations, that's what's going to give us all of the solutions. Okay, so and that is how we solve for trigonometric equations.